All right, next example. I'd like to look at a problem that involves one-dimensional forces in which we have a beam that is an extended mass that is 10 meters long, and that beam is supported at the 1 meter positions away from the edge of the beam. And so let's say that this beam is supported at these 2 points, essentially the 1 meter position and the 9 meter position if we're measuring from the left-hand side of the beam, in order to support this beam so that a painter can paint the side of a building. And so the painter then, let's say, is located at the 6 meter position. And so from this information, let's find the normal forces exerted on the beam by the supports. Okay, so here are our 2 supports. They're located at the 1 meter and 9 meter position. Here, because the beam is an extended mass distribution, we can pretend that all of the mass of the beam is located at the center of mass position. This is just perfect for the kind of application that we were looking at before in terms of center of mass. And so this works great then for torque problems. And so the mass of the beam, let's say, is 50 kilograms, whereas the mass of the painter, let's say, is 100 kilograms. And the painter is located at the 6 meter position. Now, if you were carrying a couch with your friend, and somebody put a weight, let's say, at the 5 meter position, or at the midpoint of the couch, then you would each feel the weight equally. But if somebody said, well, hey, let me put the refrigerator over here on your side, then you'd say, no, I don't really want that on my side, because that means that I'm going to have to lift with a larger amount of force. And so here, what we're going to expect, if we draw all the forces that are acting on the beam, is that we'll have a normal force here due to support 1 that we could call F normal 1, but a larger normal force because the fact that the painter is on this side. And so I'm going to, although I don't know how big that is yet, I'm going to call that F normal 2 and make it longer than F normal 1. And then we'll use the algebra of solving the force and the torque equations to determine what the values of F normal 1 and F normal 2 should be. Okay? And so the first thing that we should do, because we don't want to panic, just because this is a torque problem, is to go with what we feel comfortable with. We draw a clearly labeled force diagram in which F normal 1 and F normal 2 point in the positive y direction, and the 2 weight vectors point in the negative y direction. And so that should then add up to 0 because we are in static equilibrium. So this is our first condition for equilibrium, and we don't have any x forces here. So we can just say that the sum of the y forces is 0. So that gives us F normal 1 plus F normal 2 minus mass of the beam times g minus mass of the painter times g equals 0. Okay, so that's our first equation. That's the easy one. And you'll notice here that nowhere in the force equation do the location of the forces play any role. It's just which direction are the forces pointing that is included as relevant information in our force equation. We'll also notice here that the sum of the two normal forces can be solved for immediately. And that should make sense that the amount of force pushing up on the beam would equal the amount of force pushing down on the beam if the beam is not moving. And so that's exactly what you get if you solve this equation. It's just F normal 1 plus F normal 2 equals the total weight of the beam plus the painter on the beam times G. So that's the easy part. But now we also have to take into consideration the torque equation. Now here's the way that I suggest doing the torque equation. Step 1, choose a pivot point. And you are free to choose whatever pivot point you want in this problem, but you want to do it in a smart way. You don't want to just choose a pivot point, say, randomly that's there at pi times the square root of e divided by 10 away from the center. Because if you do, your numbers are going to be horrible. And so when you choose a pivot point, choose it in such a way as to simplify your algebra. And so that means you should choose your pivot point so that it intersects with an unknown force. Or in general, an unknown quantity. But in our example, it's going to be an unknown force. Okay, so what I could do then is a lot of people would say, oh, I'm going to choose the pivot point at the center of mass. But then you have two unknowns in your torque equation. And it's okay to choose any pivot point you want because it's not pivoting. That means that the sum of the torques around all points must be equal to 0. Because if one point had an unbalanced torque, it would start to rotate and take all the rest of the points along with it. So this is why you're free to choose any pivot point you want, but you want to be smart about it. Okay, so I have two choices then of where I could choose to make my pivot point that would eliminate an unknown force. I could either choose it at the location of F normal 1, at this pivot point, or at this pivot point here, or this point of support, F normal 2. And so I'm going to choose F normal 1. So this is going to be my pivot point. But I leave it as an exercise to you to solve this problem using F normal 2 as your pivot point. So there's our pivot point right there. So that means that all of our torques are going to be measured with respect to that point. And so when you choose your pivot point on an exam, I'll first have to look and see, well, which pivot point did you choose? Because your torque equation may look different from the person's torque equation that chose a different pivot point. Okay, so it's all relative to your choice here, but be smart about it so that you don't have a lot of extra calculations to do. If you just have one equation and one unknown, then you can solve for that one unknown right away without having to do a bunch of algebra. So that's the whole idea. Okay, so that's step 1. Step 2, this is my suggestion for these problems, is to make a table of clockwise and counterclockwise torques. As measured from your pivot point in problem 1, or step 1. Okay, and so how can you do this? Well, here I've got a meter stick, which I'll use for this problem, but you could just as easily use the pencil or the pen that you're using to write as your extended mass distribution. So what I'm going to do then is I'm going to put my pivot point here at the location of F normal 1, and now I'm going to see which direction the system moves as I apply each of these forces about that pivot point. Okay, and so what I'm seeing here then is that I get a clockwise, and a counterclockwise rotation by separately applying each force through a different radius vector. Okay, so the two masses then are going to give me clockwise torques, and the F normal 2 is going to give us a counterclockwise torque. So I'm just going to make a table of those. Now, when I'm all done, I'm going to set these equal to each other because the clockwise and the counterclockwise have to cancel out. In the book, a lot of times what they'll do is they'll define clockwise as negative and counterclockwise as positive. And that gives you the same result. But then you're stuck with this arbitrary definition of which one is positive torque versus which one is negative. Whereas the way that I do it is to just set the sum of them equal to each other, and that automatically cancels them out. And I think that it's easier to follow if you do it that way. And so that's the way I'm going to proceed here. So the clockwise torque for the mass of the beam is going to be this radius vector times this weight. Okay? And that's about this 1 meter position. And so this distance then is going to be 4 meters. Okay? And the weight vector from the center of mass weight is pointed perpendicular to that 4 meter displacement vector. So I'll write this as m mass of the beam times g times the radius vector, which is 4 meters. Okay? And similarly, for the mass of the painter, from the 1 meter position to the 6 meter position is going to be a 5 meter displacement from our chosen pivot point, which is 1 meter away from the edge, or 1 meter from the edge. So 6 meters from the edge is 5 meters from our chosen pivot point. So that would be mass of the painter times g times 5 meters. And then the third force is going to act to make the system rotate counterclockwise about this chosen pivot point. So you do this again with your pencil. Just practice doing this as I'm doing it here, just to make sure you can do it. And you can rewind the video anytime you want. That's what's great about this new system. All right, so here we've got F normal 2 times this distance here, which would be 8 meters. Okay, so that is step 2 then. I've made a table of my clockwise and counterclockwise torques. Now in step 3, set the sum of the clockwise torques equal to the sum of the counterclockwise torques. And this is the same thing as the sum of the torques equals 0, if we define clockwise to be negative and counterclockwise to be positive. Okay, so this is the way the book would say that you would do it, is you just automatically make this negative and that positive and add them together. But I'm just going to set them equal, which is the same thing. So we've got mass of the beam times g times 4 meters plus mass of the painter times g times 5 meters. So that's the sum of the clockwise torques equals the sum of the counterclockwise torques. There's only one here. F normal 2 times 8. And I'm leaving the meters off so that we don't confuse those with masses. Okay? And so now let's plug in the numbers. For the beam, we had 50 kilograms times g, 10 meters per second squared, times 4 meters, plus mass of the painter, that's 100 kilograms, times g, 10 meters per second squared, times 5 meters, equals F normal 2 times 8 meters. Okay, and so we have the units in on this step. By the way, the units for torque are Newton meter, because it's force times radius vector. And so force times a radius vector is going to have units of Newton times meter. Now we said before, when we did this with energy, that the force times the distance has units of joules. But we don't want to say that here, because the only way that you can do work is if the object moves. And yet I can apply torques, and until the object starts to move, there's no work done. So we just leave it as Newton meter, and we don't try to simplify that to joules, because that would give the mistaken impression that we were dealing with an energy concept rather than a torque. Now if you rotate an object, a mass, through an angle theta, then you're doing work because the object is moving, but not if it's in a static situation, as is the case here. Okay, so we're almost ready now to solve this problem. And we just solve for the desired unknown. In this case, we've got two equations, this one, and two unknowns, F normal 1, F normal 2. But this equation has F normal 2 all alone. So that means that we can solve for F normal 2 without doing a bunch of algebra manipulating the two equations. How do we do that? By being smart, eliminating F normal 1 from our equation. Okay, so down there then we've got 50 times 10, that's 500 times 4 is 2,000 for that first term here. For the second term we have 100 times 10 is 1,000 times 5, so that's 5,000 equals 5,000 equals F normal 2 times 8. Okay, so F normal 2 is going to equal 7,000 divided by 8. And so that gives us 875 newtons. That's F normal 2. So we have that. And so now we can go back to the first equation and solve the algebra for F normal 1. So we know that F normal 1 is equal to the total weight, which is the mass of the beam plus the mass of the painter, times G, minus F normal 2. And we're going to expect that F normal 1 is less than F normal 2 because the system is weighted to the right. And so that is the way that we can double check that our result is reasonable. So here we have mass of the beam, that's 50 kilograms, plus mass of the painter, it's 100, times G, 10 meters per second squared, minus 875. Okay, so this would be 150 times 10 is 1,500 minus 875. And so that gives us 625 for F normal 1. So is that a reasonable result? I think so. This gives us F normal 2 being bigger, 875 newtons. F normal 1 being smaller, equaling 625 newtons. And so that's the way that we would handle a problem like this by using our basic definitions of center of mass, and also by an intelligent choice of where to put our pivot point.